Okay, welcome back to the second half of Chapter 8 on graphing. We're picking up on page 245, talking about the minimum spanning tree algorithm. Often it's just abbreviated MST. Okay, so minimum spanning tree. So this is a really common thing in the real world. I mean, if you consider like a fault-tolerant network, where there's lots of different ways you can get from point A to point B, lots of alternatives. The minimum spanning tree, the job of it is basically to eliminate all the alternatives and just produce a map that just has the most appropriate way to get from point A to each one of those things. So no alternatives. So a regular graph let's just say it had 30 edges in it. When you're done with running a minimum spanning tree, you're down to just like 10 because all the rest of the paths have been taken out because you've chosen the most appropriate path, the shortest path. And when I say shortest path, I mean shortest path between each section, not between A and B kind of a thing. Like what's the shortest path between here and, between Dallas and San Francisco? That's not what we're talking about. We're talking about building a map with redundant edges removed. Okay, that's what we're trying to do. So it is used in the real world in fault-tolerant networking, where I maintain a map of how these routers are connected together. And if a router goes down, well, then I need to rebuild the map really quickly. And one of the cool things about using the minimum spanning tree, in addition to producing a map that shows all the redundant edges removed, it also makes sure that I don't have any cycles in there. So like when I route a packet, I don't want the packet to somehow get stuck in a loop somewhere. That would be really bad. Okay, so one more time. What's the difference between a traversal and a minimum spanning tree? All right, the job of a traversal is to go to every single node and, in theory, do something there. Go to every single node. It didn't really matter. I mean, there was two different techniques, right? Depth first and breadth first kind of a thing. It didn't really matter if it was the shortest path or anything like that. That wasn't his job. His job was to meet everybody. Okay. Minimum spanning tree is to produce a map. You're not actually traversing anything. Now, I'll admit, after you've done an MST, then you could traverse that thing. That would make sense. But it's not a traversal tool. It's a map building tool. Okay. So, the techniques. There's a brute force approach. The brute force would be look at every single possible combination of the paths until we finally get to the one that we want. You can probably imagine anytime you have a check every single path kind of a thing, you end up with a big O of something like this. It's just almost as bad as in factorial. So that sucks. I mean, for a big O notation, trying every single combination, that kind of sucks. So there's one, and I'm probably going to be absolutely brutalizing the pronunciations here, but there's one called Dijkstra-Prim algorithm on page 245. And before we even start talking about the algorithm, let's talk about this term called greedy, a greedy algorithm. Actually, to tell you the truth, that's probably not a very descriptive term. I'll just tell you why in just a second. So a greedy algorithm is I'm doing something and I don't have all the information. For example, I don't know what the map is going to look like at the end. So I haven't collected all this information. So I'm making decisions based upon what limited information that I have. That's the greedy part. The greedy part means I'm not waiting to the end to make the final decision. I'm making many incremental decisions along the way with the best information that I've got. Okay, so instead of being greedy, perhaps a better would be incremental or impatient or something like that. Because, one more time, a greedy algorithm basically says I'm making decisions along the way with the best information I got, and if I make a mistake, I'll turn around and go back. Just like navigating a maze, right? Oh, I think I'll turn to the left. I made a decision, right? And so I go, well, shoot, that didn't work. So you backtrack and, okay, now I think I'll go to the right. You're making decisions as you go. And if you come across a dead end or something, you just backtrack and keep going. So that's a greedy algorithm. So in our case, what we do is we we keep the shortest path as we going along and throw away all the others that don't meet that criteria, right? You know, if I have 2 ways to get there, I'm going to obviously keep the short one and throw away the long one. Okay. So, during the process, each node is put in a tree, and then it's on the fringe. So it's either in the tree, it's on the fringe, which means I haven't got to it quite yet, or not seen. So it's on the tree, it's a fringe, or I've not even seen this node yet. I mean, because I'm making greedy type of decisions, so I haven't even got to that guy yet. I don't even know that guy exists yet. Okay, so here's how it works. You pick a starting node, and quite frankly, it doesn't really matter what node, because you're building a map. Remember, you're not traversing. So build a map. In this particular case, fine, we'll use A. I mean, you don't have to use any one particular one. So you start off. So from the viewpoint of A, the greedy part would be, I can only see B, D, F, and C. That's the only thing I can see, right? So I look at all those guys, and then so that's as far as I can see. And then I make a decision on how I'm going to make the next step. So I'll admit the decision may be wrong, and you might have to backtrack, but that's okay. And so I didn't show all the other things. There's, A and B. There's also a C and a D and an H, all the rest of those letters where they get a little bit closer. But you see how this thing works. Pick any point, and then look at all the things you can see and make a decision, and then do it again, and then throw away the bad ones and keep going. You'll end up, this is the first iteration, and obviously there's an awful lot of more iterations not being shown here. But this is what you're going to end up with, the 8.5H. This is the map. This is the map of so I have reduced this. Look at all the number of edges that are in here, and now I've reduced it down to this. Okay, so that's the purpose for this guy, right? A minimum spanning tree is to remove all the redundancies. So I still have the same number of nodes as in A as I do in H. I just remove the ones that aren't as efficient. Cool? Okay. Whew. So, here's how it kind of sort of works. They have some pseudocode on page 246, but it is very, very much pseudocode. It's practically useless. So I'm going to give you kind of a narrative on how it works, and then we'll go look at a real implementation. So, you pick a starting node, and once again, it doesn't matter which one you pick because you're building a map. Add it to this tree, and then all the connected nodes are now considered fringe. That's why they're shown in a dotted line, because they're fringe nodes. And then add another node to the tree, and then throw out the longer ones, and then update the total distance. So here, the total distance, the 4, the 5, the 6, the 1, the 2, and the 3, the total distance is what I'm after. Okay? Good. All right. So they do show the pseudocode for doing this, but this is useless. Pick a starting node, build initial fringe, connect, blah, 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 blah. If you really want to see how this thing works, you're going to have to go to a couple of websites where you can get a real honest-to-God algorithm. So this is some really cool stuff. I actually would, this is in the lecture notes. You probably need to go here and then kind of get an idea how this thing works, and then the code to make it work. So yeah, I mean, this is good stuff. This is exactly how you do this. So they have implementations in C++ and C and Java and Python and C#. So that's pretty doggone cool. I think that'll probably just about cover it. So this is how it's done. So when it comes time to doing this in like a homework assignment, yeah, you've probably basically already have the algorithm done for you. Okay, cool. Now for the complexity point of view, the complexity part is complex. Oh, sorry. If you're stored in a matrix, then it's going to be n squared. Okay, if the underlying data is in a matrix. Remember we talked about the adjacency matrix? But if it's stored in a linked list, it's actually a little bit better. it would basically be, we're talking about the N is the number of nodes and E is the number of edges. So this would be E times log of N if it's done in a linked list. Okay, which means if you had to decide which of the storage technologies you should do, you should check to see if I have more edges than I have nodes. Well, how obvious is that? I mean, is that a very common thing to have more edges than nodes? Well, yeah, pretty much. I mean, you know, if you consider a street map, an intersection, right? An intersection between two roads, that's one node, but 4 edges, right? So yeah, I expect to have a heck of a lot more edges than nodes, typically. Anyway, so kind of sort of depends. All right. So the next thing we're going to talk about is another technique, Krustal's algorithm on page 249. Now, Dijkstra-Prim starts with the nodes, so it's kind of node-centric. Pick a node and put it on a tree and then go find the edges, and it's node-centric. The Krustal is edge-centric. So it starts with sorting all of the edges and then going through. So it's just a completely different way of thinking about the same problem. Do I start with edges or do I start with nodes? Okay. So here's how it works. Again, I'm going to go through the narrative because their pseudocode is useless. So you sort all the edges, okay? Pick the shortest edge to start with, add it to the tree. It doesn't matter if the nodes are connected at this point. That's not what we're doing, So you just start adding edges, and then pick another edge, and then add it to the tree. And if it does not create a cycle, cool. Throw out the longer options. And that's basically how this thing's supposed to work. So here's how it works. And again, this is not all of them. So here's the list and say, ooh. If starting with 1, it's because that's the sorted one, right? So I do this one, and then the next shortest one is that one, and the next one is that one. And so you just keep adding these things in until either it doesn't create a loop, or you have duplicates and you throw one away. Not duplicates, but you have an alternative when you throw the other one away. Okay. Again, the pseudocode in the book is pretty much useless. Yeah, it talks about a tree and finding the root and all that stuff, but certainly nothing that you could implement. On the other hand, the good old Geeks for Geeks has got this, and they explain it in detail, and they give you all the source code in Java and Python. So once again, you have all these really, really cool, already worked up examples for you to work with. Okay? Cool beans? Good. Okay. Now here, the complexity is going to be back to this. Oops, no it's not. It's actually E times log E. Because remember, this is edge-centric, not node-centric. Okay, sorry about that. All right, so one more time. Which is the better approach? Is the Krustal or the Dijkstra-Prim technique? Which one is the best? Once again, the answer is, do I have more nodes than I have edges? And so, depending, if you need to know a little bit about your graph before you decide to pick which one of these things which one of the techniques you're using. If I have more paths and nodes, like a typical street map would have, but if it's like a network kind of a thing, maybe not. I mean, you might just have lots and lots of one-to-ones. Okay, now we're coming up on the 15-minute mark. You guys know how this works.